In the previous video, we defined a unit vector as a vector whose magnitude is equal to 1. In several applications, we want to operate with unit vectors. And so we need to be able to find a unit vector that has the same direction as whatever vector we're working with. Obviously, the unit vector won't have the same length, magnitude, because a unit vector has a magnitude of 1. But if it has the same direction, that can be useful information. So the way we find the unit vector that has the same direction as v is we take the vector v and we divide it by its magnitude. So the vector divided by its own magnitude is going to convert it to a unit vector that goes the same direction as the original vector. So let's look at example 10. So the first thing we have to figure out, if I want to take v and convert it to a unit vector in the same direction, then the first thing I need to do is figure out the magnitude. Now remember, that's just good old Pythagorean theorem. So here's what we should get. The magnitude of vector v is 13. And so now our unit vector, and there's not really good notation for this. There may be something that they use in physics that I'm not aware of, but the unit vector is going to be vector v divided by 13, which means we're just going to divide each of the components by 13. So you get 5 over 13 times I minus 12 over 13 times j. So that one is going to be going the exact same direction. It's going to be going to the right and down, but this one is only going to have a magnitude of 1. Now, these examples say, then verify that the vector has a magnitude of 1. So I'll just show you on this one. You don't really need to do that. But if we go ahead and find the magnitude of this unit vector, here's what that would look like. Gets a little bit uglier with the fractions and the exponents, but we still end up with a magnitude of 1, which is why this gets to be classified as a unit vector. So pause your video and try number 11, and I'll be back in 3 seconds with the answer. There it is, 4/5 I minus 3/5 j. And then again, you could go ahead and verify using the Pythagorean theorem on this one that it does in fact have a magnitude of 1. So once we figure out the unit vector, that helps us figure out how to write a vector in terms of its magnitude and its direction, okay? And so let's look at what that is going to look like. And this is where some of your trig comes back in. So if we have the vector v expressed as ai plus b times j, then the components a and b can have a magnitude of v and the angle theta that v makes with the positive x-axis. So remember that these are angles that are going to be measured in standard position. So that means that we have to start from the x-axis and rotate in the counterclockwise direction, okay? This angle is referred to as the direction angle of the vector v. And knowing what we know about sine and cosine, using opposite over adjacent and whatever, then you can see over here how they have derived the following formula. If this is how we get the component for A and this is how we get the component for B, then finally this vector of A times I plus B times J is going to look like that. So the way that we can write a vector in terms of its magnitude and its direction, meaning using the angle, is going to be that V is equal to the magnitude of V times the cosine of theta, I, plus the magnitude of V times the sine of theta, J. And so it kind of makes sense with what we know about how the cosine corresponds with your x coordinate and the sine corresponds with your y coordinate. So let's look at an example of how you might use this. And so now we're starting to get a lot more physicsy here. So those of you taking physics right now might be kind of glad that this might be stuff that you know. So a vector that represents the direction and the speed of an object in motion is called a velocity vector. So I think this is one of the first things that your physics teacher probably drills into your head, is that speed is a scalar, meaning the direction does not matter, and velocity is a vector, which means the velocity does matter. So typically, if our velocity is going to the right, it's a positive velocity. If a velocity represents that we're moving towards the left, it's a negative velocity. Speed doesn't have that. If you drive 50 miles an hour, the direction doesn't matter. So velocity is always going to have a direction to it. So number 12 says, the wind is blowing at 20 miles per hour in the direction north 30 degrees west. There's a bearing. Express its velocity as a vector v in terms of I and j. So there's two things that we need. We need the magnitude and we need the direction. And both of those things were given to us in the problem. The sort of like strength of your force, our velocity in this case, is the magnitude. So this 20 miles per hour that they gave us, that is the magnitude of this particular vector. Okay. Then they gave us this value here. Now, this is a bearing. And remember, bearings are measured differently than angles in standard position. So we have to think about how we can get the correct angle for theta, because it might be 30 degrees, but it also might not be. So let's take a look at that. So here's our compass. North 30 degrees west would be a bearing that would look about like this, okay? And this angle here is 30 degrees. However, this angle in standard position would start on the east line and go all the way around. So the angle theta that we really need is this right angle plus the green angle that's 30 degrees. So it's going to be 30 plus 90. So the angle theta that we want to work with here is really 120 degrees. So you always have to be careful when they give you a bearing. If they just gave you an angle, you can assume it is in standard position. But because bearings are measured from that north-south line, you might have to do a little bit of tweaking to figure out what that needs to be. So the theta that we want to use is 120 degrees. So again, using the formula that is right up here, our vector v is going to be the magnitude of v, which is 20, times the cosine of 120 degrees. And that's all times the unit vector I, plus, again, 20. The magnitude is not going to change. And this time it's times the sine of 120 degrees. And that's all going to be times j. Now you can go ahead and put that into your calculator. 120, those are numbers that we know from our unit circle. So in calculus, that very well might be a no calculator question. And I left my answers in exact form. So this is going to be 20 times the cosine of 120 is negative 1/2 times I, plus 20 times the sine is square root of 3/2 times j. And so that simplifies down pretty nicely that v is going to be negative 10I plus 10 square root 3 j. Now, the only reason that I put those parentheses there is so that the j doesn't get muddy with the square root of 3. I want to make sure it's clear that the j is outside of that, so that's why I put parentheses just for clarity. So there is another one just like this on the next page. So take a second to read through the next example and see if you can kind of start gathering the information. See if you can pick out the magnitude and see if you can pick out the correct angle theta. So hopefully I identified that the magnitude is 60. And then this one, it does end up being the same simply because 45 is exactly half of that 90 degrees. So north 45 degrees east really measures this angle right here. So theta, its complement, is also going to be 45. So now see if you can go ahead and set up this equation and find its exact value for vector v. And this is what you should get for your final value for vector v.